an issue that I have is that I have a lot of ideas. So let's start implementing those ideas. So the first game I started with was something simple. It's based on Connect 5. Ignore the fact that it's called Connect 4. And what you have to do is that you need to have 5 units in a row or diagonal or column in order to score a point. So if we were to play a game, then I would place one, then the enemy places one, and then I will place another one, and so on and so forth, till someone gets 5 in a row. And then the one that gets to 0 loses the game. And then you can go again. So this was the first project or the second project that I actually finished. And this video is about how we can build it. I have some steps here. So I tried to reconstruct the game that I built, and these are all the steps that we need to go through. So let's get cracking. Let's get to it. Okay. And the first step is being able to draw the map. So first, let's create a folder named assets. Then we'll drag over the resources. This is the board. That's good. Now let's create a scene. We'll call it main scene. Save. Then we add a child node. Nodes. Tile something. Tile map. That's good. New tile set. Boom. And then we need to make a new tile set from the board. So we click Atlas, Assets, Board. I think these are 32 by 32. So we have to modify it here, 32, 32. Then here again, 32, 32. Good. Now what we have to do is create an auto tiler. Terrain set, add new terrain. Yeah, because they changed the name in Godot 4. Add element, blah blah blah. We call it board. Board. Good. And now we select terrains. New terrain set, terrain board. Good. I think we have to select those. Yep, and now we start drawing. So now the rule for drawing is that each tile set needs to have the center square selected, because that's the square representing the actual tile. Now the rest of the selections are based on what the neighbors look like. So in this case, we have a tile in the right. This one has a neighbor on its right, on its left, on its bottom, and then also has on its right diagonal and in its left diagonal. So this is how you set it for this. Then you go for the other one, and you have one underneath, one on the right, and one on the diagonal. And then you do the same for all of them. Done. So now if we were to go to tile map and terrains and board, and you select this one. And it looks ugly because it's not made to support different weird shapes, but as long as you draw a square or a rectangle, it should fit in nicely. Okay, so let's do something. That was easy. Okay, so that was the first step. We have the map. Done. Then there's the next step. Can detect clicks on the map. So what we're going to do is that we're going to create the script on the main node. And then let's see. First, I think we'll need to do the mouse input event. So let's add that. So project settings, input, left mouse click. And let's also have right mouse click. Then okay. So the way that I automatically selected it is that you select this box, and then whatever key you're pressing is going to be automatically detected here, because otherwise you'll have to scroll through all the buttons and then find the one that you're looking for. And then we need a position. Let's use it here. Var mouse position equals to get global mouse position. Good. So print, let's test that this works. Select currency, whatever. Boom, 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 boom. Okay, works. Okay, so right now we have clicking and we get a mouse position. Good. Now the next part is to get the tile corresponding to the mouse position. So that should be easy. First we need the reference to the tile map. Actually, let's do something. Let's do it like this. Export tile map. Tile map. Export var. Doing crazy stuff. Okay, so now you have to select the tile map from here, and that's it. Okay, super. And then we have the tile map. The next step is to get the cell corresponding to the mouse position. Well, first we have the mouse position, which is actually the global position. We have to transform it from the global position into the local position of the tile map. So we do tile map dot to local of mouse position. In this case, it will be the same because they have the same origin. But if we were to move the tile map, then I think it will change. So let's check it. Var, what should we call it? Tile map position. Tile map position. Good. Oh yeah, let's print them. Print mouse position. Bum bum. Tile position. Good. Play. Click, click, click. And they're exactly the same. So if I were to shift the map, I think they'll change. Let's check that just for the sake of it. So if I were to take the tile map and move it, and I started clicking, yeah, now they're different. But they should refer to the same position. It's just that one is relative to the entire game and the other one is relative to the tile map. Going forth. Okay, now we have the position relative to the tile map. Now what we want is the cell. Click cell equals to, that's it. Click cell. Yeah, and now if we print it, click cell. Can detect clicks on map, done. Nice. But we will have to do some stuff here such that you won't be allowed to click anywhere. Like it's too permissive to click anywhere here. Thing is that you have a board, you have a square on the board. If you click here, it's going to be counted as if you clicked here, which is not correct. What we want to do is, rather than having you click anywhere inside the box, have a max distance, and if you go too far from the center, then it's not a valid click. But if you're close enough to the center, then it's like, okay, you wanted to click here, but you don't have good precision. So this is what this function does. It checks this one position with another one, where one position will be the center and the other one will be the mouse position. Which means that right now what we have to do is get what's the center of the cell in global, so we can compare it to the mouse position. Okay. Let's see. false, 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 true. Okay, true. Let's actually put this in a separate function, func. Good, good, good. Okay, so we have this. Now the next step is to have a unit that we can place. So let's do that. Let's call this one token. Token scene. Bam. And then let's make it simple. Let's just call a sprite 2D. Icon, drag it here. Now we have an icon. I don't know how big the icon is, so let's drag it here. Okay, so that's way too big. I think the cell is 32 by 32, so let's try to make this 16 by 16 just so it fits. Is my math okay? Yeah, seems like it. Good. Create a constant. Let's call it token. Token scene equals to preload token, and then every time I click somewhere, if is valid mouse placement, is valid placement, sorry, then we create a new child. So it should be var token equals to token scene instantiate, where and we want to add it as a child to the tile map. So it's tile map dot add child token. Nice. But we also have to set its position, and its position is token dot global position equals to, actually let's take the mouse position. We'll see whether this works or not. No, because we have to do it position. So because it's a child of the tile map, it shares its axis origin, so we can use the tile map position, and this will help us later on when we're gonna move this into a we're gonna move all this code in a separate function. Good. Yeah, that's it. Let's see if it works. Boom, boom. Oh, right. If we use the mouse position, then it's going to be, if I click here and then here, they're gonna be a bit shifted. So rather than using the tile map mouse position, I think we need this. Damn. Okay. Let's then move it here. And then is valid placement doesn't make sense anymore. We can just call r close enough here of tile map position and this, and then we can get rid of this function call, and then we use the tile map cell center. Let's see. Boom, boom. Boom, 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 boom. Okay, so they're a bit too big. Let's make them a bit smaller. Let's divide by 5. So that's 0.2. Let's check now. Still a bit too big, but I think it's good enough. Does it work here? Yep, it also, yeah, they're a bit too big. Let's make it 0.15, because maybe that's a bit too small. Okay, that works. Nice. Okay, so now we are able to place stuff on the map, but there's one issue with that. If we were to go to remote and see, so now we have no children attached to the tile map, but if we click on the same spot multiple times, it just adds a lot of cells there and a lot of tokens there, even though the cell is theoretically occupied. So what we have to do next is to also mark the cell as being occupied, so we don't click it twice. 1 second. Good. So now the next step is to check whether the cell is occupied. But in order to do that, we must first add some logic to make the cell occupied. How do we do that? Good question. We're gonna do set cell. Oh, now we need to set a lot of variables here. So the first is the layer, then the coordinates and the source of the cell, and then the atlas coordinates and alternative cell. So there's a trick here. So first, the layer. I think we should create another layer. So we have a. Where are the layers? Where are the layers? Terrain set, navigation layers, custom data rendering, resource? No. Layers. Oh, right. Okay, so the first one is the board. We don't touch the board. And then the other one are the tokens. Good. Now we have 2 layers. So we need to specify a constant tile map token layer 1. I think, is there any way to check the index? Layer 1, okay. Good. So now we have the layer. Boom. Next, coordinates. Which cell of that layer do we want to set? What we need is the clicked cell. Good. Next, source ID. Okay, so ideally what we need is to set a cell. But if we set the cell, then let's see. We can actually do something cheeky and just set it like this. Okay, this is why we added the other layer, because if you set the cell on the board, then you just remove the map. So we set another one, and then you just click it like this, and it works. We can actually do this. Yeah, we should do this for now. So the coordinates are 3, 0, and the source is 0. Let's do that. Let's set them somewhere so we don't forget them. Const occupied cell ports, whatever, vector 2, and it says it's 3, 0. So we have a set cell of tile map, tile cell, blah blah blah. We need the source. Was it? What was the next one? Yeah, source. So let's call source of 0 because we only have one. What does it say here? Yeah, source 0. Then we need the atlas coordinates, which is occupied cell coordinates. Okay. Okay, so we set the cell with something. And if we did it right, even though if we put something, yeah, we cannot see the small shadow. But we still have, we can still place a lot of tokens, even though the cell is occupied, right? No? Oh. That's weird. I thought we had to do an extra check. No, it still reproduces. Okay, that's good. I mean, it's not good, but it's good. It's expected. Okay, so we have here 1 check is close enough. Okay, so now we can do the function func is valid placement. What we did here is we first check whether the click position is close enough to the center of the cell, and then we check whether the cell isn't already used, like we haven't already placed the token there. So now if we go into remotes, tile map, and then here, and we... It doesn't let me place at all. Why come? How come? Not in. Not in. So if the cell is not in. Okay. So now if I spam it, it won't put another one, but if I click into another position, it will. Okay. I'll call that good. So this one is done. The next one is to detect whether neighbors are near the unit. Okay, this is token in our case, it's not unit. But before doing that, let's clean up the code a bit. Let's create a let's call it board.gd. Let's create a script for the tile map and then move all this logic there because it's cleaner that way. Place token at position. Boom. Token scene. And it should behave exactly the same. Okay, so what was the next step? Can detect neighbors. Okay. Yeah, right now we just place stuff. But the next step should be for us to see when two cells are neighboring. So in this case, you have only one neighbor on the right. This one has no neighbors. This one now has two neighbors, one on the left, one on the bottom. But we can also do diagonals. So in this case, the last cell I placed has three neighbors, 1, 2, 3. Okay, let's do directions. Let's do columns. So first, let's define a constant. Y-axis is like you have your north point and your south point, or up and down. Okay. So what we want to do now, let's create a new function. So let's go here again. If you have one cell here, okay. So the coordinates for this one, let's say it's vector 2 of 0, 0. Then the coordinates for this one are vector 2 of, was it -1, 0? -1, 0. Yes, okay. Which is also equals to. So let's actually call this something. Let's call it C1. And this we'll call C2. So from this, what we can do is say C2 equals to C1 minus vector 2 of 1, 0. But vector 2 of 1, 0 is, which is also equal to C1 minus vector 2 dot up. So that's what we're doing. We have, so this should be minus shift var, and here var. So shift is y-axis of direction, where, so we practically iterate through these and we get the north and the south. So we get vector up, and then we get the cell from above, and then the cell from underneath. So if we were to do print neighbor cell, it gets me the cell from above and cell from the underneath. What we also want to do is to check whether the cell is occupied. So we do if neighbor cell in get what's it called? Used cells. Yep. Again, the layer tile map token. I should actually rename this. Let's call it only token layer. Give me 1 second. Control C, Control D, delete. Boom. Now I replaced it everywhere. So if neighbor cell in get used cells of this, print. So only if I have neighbors there will I print it. So now nothing. Now I have one underneath, so it prints. So if I do this, it should print 2 times, and it does, which means it works. So we can detect neighbors of a unit, which we do. Do we want to do it on all directions? Let's just keep on y-axis for now, and then we'll do the other directions. What's next? So next we want to check whether we have 5 units in a row, column, or diagonal. If we have 5 in a... Okay, so what happens right now is that if I place one here, it says it doesn't have any neighbors. If I place one here, it says it doesn't have any neighbors. If I place one here, it says it has one above and one underneath. If I place one here, it only tells me that it has one above, when actually it has 3 above it. So what we want to do is have a way for this to tell this one to check above, and this one to check above, and this one to check above, and then return how many it saw above it. So we have to do like a chain reaction. So in order to do that, we have to use recursivity. I don't know how to call it in English, but we have to do a recursive call. So first we have to do func, and we know what direction, which is up or down, which means all this code has to go somewhere else. So we do func of boom boom, and then what we need here, this has to go backwards, and then we need the tile map cell and the shift. What we're gonna do is that we want to do a check, see whether it has any neighbors, which is this, and if it has any neighbors, tell its neighbor to also look in the same direction, which means we have to take this, and rather than tile map cell, we call for a neighbor cell, and we also do a print. Here 1 2 2 1 2 3 1 2 3 4 1 2 3 4 5. Okay, actually, yeah, let's just have a counter for now, and then we're gonna iterate on it. Neighbor count equals to 0. So if neighbor cell and get you cells, then we return here. No. Then we have neighbor count plus equals to 1. And then we return neighbor count plus equals to this. No, plus this. Otherwise, we just return neighbor count. Does this work? Let's see. For neighbor count, print neighbor count. 1 2 3 4 5 6. Okay, it works. The thing is that we don't count ourselves, so we only count neighbors. So +1, because that's ourselves. So now we have 1, 2, 3, 4, 5. Nice. What's next? We can do this. So can't detect neighbors. This is done. Can detect when there are 5 units on a row, column, or diagonal. Then you print, you win. Okay, we don't do that yet. So let's do a check. Let's have a constant here. Constant. Let's call it min connections equals to. Do we have 4 or 5? Let's do 4 because it's easier to test. Let's move it here. Min connections 4. Let's actually have 3. Let's have 3 because it's easier to test that way. You can change the number as you want afterwards. So we have if neighbor count plus 1 is greater than min connections, greater or equal to min connections, then print you win. 1, 2, 3, yay! And I keep on winning. What happens if I go 1, 2, 1, 2, 1, and then click here? You win, yay! Actually, yeah, this is not fully correct because we have to count all the connections. Yeah, because you have 2 above, 2 underneath. If you do, let's increment it to 5, and I'll show you a bug. So if I go 1, 2, 1, 2, this won't be a win even though you have 5 in your column. So this is not okay. What we have to do is var total count 0. Then you go total neighbor count. I'll just do neighbor count. Neighbor count plus equals to whatever this returns. We get this out of the way, and this should work because now we count both above and underneath it. Yep, now it says you win. So this works. What was the other thing? We have to check on row, column, or diagonal. Okay, let's define the other ones. I'll just copy paste it from here because I'm too lazy to write them down. So we have, this should be x-axis. Left, right, diagonal 1, diagonal 2. Okay, so, but we cannot check it here because then it won't be fair because you have if you have, it's not fair if you counted like 1, 2, 3, 4, 5, 6, whatever connections. This shouldn't be allowed, at least in this version. If you want to make your own game and you wanted to have this kind of connections, you can do it. But for now, we will just count it in rows, columns, and diagonals. So what we want to do is and then we have to use here axes. Good. So now if we were to do diagonals, 1, 2, 3, 4, 5, you win. Or columns, 2, 3, 4, you win. Or rows, you win. Or the other diagonal, you win again. Okay, so it works. Done. Now the last part is that you have to check, you need to let your enemy place something on the board. Okay, so I'm gonna hack this a bit. We're gonna do, we're gonna make another scene. We'll call it enemy token. Enemy token. And the only difference that it has, if we were to go on the scene, open enemy token, open the sprite, go to material, or is it texture? Visibility, modulate, boom, boom. Now it's red. Now you know it's an enemy. Another thing what we want to do is add it to a group. We'll call it enemy. And then the other one we're gonna call ally. Oh, did I do it again? Yeah, I set the sprite rather than setting the parent. Okay, we need to have this for, this will be ally token scene, and this will be enemy token scene. And then ally token scene should be here. And then if we do if again and say right mouse click and say enemy token scene. Something's not right. I'm pressing right click, but they're the same color. What happened? Oh, is this okay? Enemy token scene. Okay, now it's red, and the other one is like that. But there's one issue with this, is that even though they're different colors, it still says you win, which can be a bug or a feature. It depends on your game. But for our game, we want to only count. For our game, we only want to count the ally tokens and the enemy tokens separately. We need a way to reference the scene that we create. So when we click here and we go to remote, we see that there is a token scene which is instantiated, and we have to have a way to refer to this scene somehow. Like when we need a way to know that clicking here, this cell corresponds to that scene the same way that this scene corresponds to that cell. We can go token reference. The key is the cell and the value is the instance of the scene. Okay, so token reference, blah blah blah. Then we here when we created, after we set it, token reference click cell equals to token. Get the token reference. We have the token reference, which tells us what's the instance for each cell, and then we get the groups for those. The groups that we set here. So this is an ally, this is an enemy. We get the groups and we get the first one, because it doesn't make sense to have an entire list. We just need the first element of that list, which will be the ally or the enemy name. So let's actually print it so I can show you. Print token type ally. Good. Actually, we can do this. We can do it here. Yeah, let's do it there, because then we don't need to access it multiple times. So it'd be check for connections and this direction for this token type. And then we have a token type here. Okay, so why did we do this? We want to check for connections only for a token type, and then check for neighbors in direction for this token type again. So we also have to put it here. Good. And then we need a way to var is in same group equals 2. Then we have to do the same thing that we did. Where is it? Where is it? Check for connections. We have to do this again, but rather than having, oh, it's fine. Neighbor cell. If the neighbor cell is in the same group, yeah. I'm stupid. I knew it shouldn't be that way. For some reason I didn't do it that way. Some things can be optimized, but we ain't got no time for that. The video is already too long. Okay, so it seems like it works. That's a wrap. This is how you can build a Connect 5 in Godot. Connect X, because you just have to change this number here. Hope you liked it. If you did, tell us in the comment what you like. If you didn't, tell us what you didn't. If you have other weird ideas of stuff we can implement in Godot, you can also write that down. So have a nice day and see you in the next video. Bye.